Hello and welcome to another Lunch and Learn at TELUS Science Museum here in Cartersville, Georgia. I'm so glad you're joining us today. We have an exciting program this afternoon. I'm David Dundee. I'm the astronomer and also Director of Education here at the museum. And I wanted to let you know about some exciting events that are coming up here at our Science Museum. As we move on into July, which starts tomorrow, by the way, we have Ask the Expert. It's another virtual program. It'll be at 2 o'clock in the afternoon on Wednesday the 7th. We have Matt Franzak, who was a retired meteorologist, was with Delta Airlines for over 30 years. They're a meteorologist, and his program that afternoon will be What Does a Meteorologist Do? So if you'd like to know what a professional meteorologist does, you need to tune in there and find out, and you'll be welcome to ask him some questions that day. And then once you have your appetite whetted on meteorology, we move on to that weekend on July the 10th. We have Wild About Weather. Yes, here at TELUS, we have a whole day devoted to weather. And so we have a number of fun activities for families to do with weather. We also have that day 3 speakers talking about weather. Matt Franzak will be back, and he'll be talking about the weather of keeping people safe traveling with weather, so meteorology and aviation, and that'll be at 3 o'clock. At 1 o'clock, I'll be talking about weather on other planets, and that'll be fun. And then at 11 o'clock, we have Glenn Burns, chief meteorologist with local WSB-TV here in the Atlanta area, and he will be talking about predicting stormy weather. In fact, Glenn will be back with our next Lunch and Learn on July 28th and talking about going behind the curtain, talking about broadcast meteorology and what it's like to be broadcasting meteorology on the news. In addition to that, on July 17th, we have our next Build and Blast workshop where you get to build rockets and hear from our local NASA ambassador about the latest rocket programs with NASA. And then you get to launch your rockets and you get to take your rockets home with you. That's pretty cool stuff. And you can register online for that workshop. And if you're 8 or older, we have a whole week of adventures in archaeology. We're partnering with Emory University, University archaeologist Megan Kilgore, and we'll be doing archaeology activities the week of July 12th through the 16th. And so if you'd like to sign up for that week-long workshop, you need to tune into our website, and you'll be able to sign up for that. Well, this afternoon, we have the honor of hosting Dr. Lynne Jones. She is the performance scientist for the Vera Rubin Observatory, a legacy survey of space and time. Currently in Victoria, British Columbia. She was part of the survey detection panel of 2010, the NRC committee to Seaview near Earth object survey and hazard mitigation strategies, keeping us safe from asteroids, in other words. As part of her work, Dr. Jones evaluates the scientific performance of observing strategies, including potential for studying small bodies with the Next Generation Telescope. She received her PhD from University of Michigan and has conducted surveys to discover some of the faintest known trans-Neptunian objects, and Dr. Jones will be talking about that. And Dr. Jones right now serves as an advisor at the B612 Asteroid Institute. And so with that, I want to welcome Dr. Jones to our Lunch and Learn. Thank you so much for being with us today, and we are excited about hearing about the latest on asteroids and maybe a little background about asteroids as well.
Thank you. Thanks, Steve. I am happy to be here. So, thank you very much for having me. And also, I would like to just make a quick comment to say thank you for B612 Foundation. They, with their sponsorship of Asteroid Day, which is today, they are raising awareness of the possibility of an asteroid impact, and they're working towards mitigation of any such event. So today, I'm going to talk about asteroid discovery. So first, I'll go through a bit of history and bring us up to where we are sort of at present. And then I'll talk a bit about the project that I work for, the Rubin Observatory's Legacy Survey of Space and Time, and how it can contribute to asteroid discovery in the future. So, the first asteroid, starting at the start, was the very first asteroid was discovered in 1801 by Giuseppe Piazzi, and this was Ceres. Two more were discovered in the following year, 1802, and that was Pallas and Juno. So these were very large asteroids, and they were discovered in the main asteroid belt. So this is where most of the asteroids are. It's the region between Mars and Jupiter. So these are asteroids that are orbiting the sun between Mars and Jupiter. The illustration below shows Ceres' orbit. It's maybe a little bit faint. I hope it's not too faint to see. But it looks fairly circular between Earth and Jupiter, or Mars and Jupiter, and it's tilted somewhat with respect to the rest of the solar system. So let's take a second and talk about where most asteroids are, what they are, and where we usually find them. So asteroids are basically small rocky objects. This is what distinguishes them from comets, which are mostly more icy, and also their orbits are different. Most asteroids orbit the sun between Mars and Jupiter. These are called main belt asteroids. It turns out asteroids can orbit in this region of space longer than the age of the solar system for the most part, and so that's why there are so many in this location. They don't tend to collide with planets or get kicked out of the solar system or into the sun very often, so they're just still there from the period when the solar system was forming. The main belt asteroids are shown as green dots in this illustration, which comes from the Minor Planet Center. The Minor Planet Center is a group which keeps track of the orbits of asteroids, fits observations so that they can update the orbits of asteroids. And they're basically just a big clearinghouse for the entire solar system. The plot shows the positions of the currently known asteroids. So the fact that those green dots show up as basically a big green torus reflects how many there are that we know about. In reality, there's still space fairly far apart. Space is big and this plot is small. So far apart, they hardly ever collide, and you could definitely fly a spaceship through this area without running into one. Now, some asteroids have orbits that take them closer to the Earth and closer to the Sun. These are called near-Earth objects, or NEOs. These are generally asteroids from the main belt, which were on orbits which were slightly unstable, so they did drift onto orbits which took them further in towards the Sun. NEOs tend to have lifetimes which are shorter than the age of the solar system, so they will eventually collide with a planet or more commonly fall into the Sun. NEOs are the group of objects which have orbits which take them closer to than 1.3 AU to the Sun. For reference, the Earth has a fairly circular orbit at 1 AU. A subset of NEOs comes even closer to the Earth. These are objects which come within 0.05 AU, or just under 20 times the distance from the Earth to the Moon, within the Earth's orbit. So these particular subset come closer than 20 times the distance to the Moon to the Earth's orbit, and they are larger than 140 meters in diameter. That's sort of a cutoff where we think if they were larger than this, they would cause regional-wide damage if they hit the Earth. And these are called potentially hazardous asteroids. There are many fewer of these kinds of asteroids, though. Again, on this plot, they look like a red ring. The NEOs are the red dots, but they are still distributed far apart from each other in space. So this is telling you just generally, where are the asteroids that we're finding? Where are they in space? From there, let's go back to how asteroids were discovered. So those very first asteroids were discovered 1801, 1802. discoveries proceeded slowly but surely through the 1800s. And this plot here shows the number of asteroids which were discovered in each year. So Ceres, Pallas, and Juno, those first three, are way over on the left. Then there was a bit of a break and a bit of another break. And eventually, asteroid discovery picked up again around 1845. And then regular discoveries happened over the second half of the century. Now, what's interesting to me is most of these discoveries would have been made by eye, making star charts by hand and looking for point-like objects moving with respect to the background stars. This is the defining characteristic used to identify asteroids in most images. While stars remain fixed with respect to the other stars, asteroids, like planets, move and wander across the sky. So these telescopes would have been a mix of refracting and reflecting telescopes, getting larger over time as techniques to cast glass and polish metal improved, and as telescope designs matured. The first NEO was discovered during this period. That was Eros in 1898. Toward the end of the 1800s, astronomers started using photographic plates to capture images of the sky. This was a tremendous advantage because now you are no longer limited by your eyes. Photographs can capture longer exposures, meaning fainter objects could be seen. In addition, star charts no longer had to be made by hand to look for moving points of light. Now the photographic plates could be loaded into a blink comparator, which is a machine that flips back and forth between photographs taken at different times to look for the moving objects. So note that the plot here, this is still, again, the number of asteroids discovered in each year, has a peak that's 10 times higher than the maximum reached in the previous 100 years. So also, about 10 times more asteroids were discovered during the first 90 years of the 1900s than in the previous century. Now, it's worth commenting really quickly. Pluto, which is let's say it's a dwarf planet, which is what it is, very similar to a very large asteroid in terms of its size, was also found using a blink comparator. And so this image on the right is Clyde Tombaugh, who was the discoverer of Pluto, and he is standing here at a blink comparator at Lowell Observatory, and probably demonstrating how you flip between plates to find these objects. So this is still a very labor-intensive way to find asteroids. You have to take plates at the telescope, develop the plates, load them into the blink comparator, and then blink back and forth between all of those images. Oh, I did want to point out, one of the other things that happened in this time period is that many of these asteroids were actually discovered in a dedicated survey called the Palomar-Leiden Survey, which ran in 1960 with follow-ups looking for specific kind of asteroids in 1971, 73, and 77. And you can see those peaks when that survey was active in that plot, especially the 1960 survey. So the addition of photographic plates and especially dedicated surveys meant that asteroid discovery could advance rapidly during this period. Then we come to the early 1980s. So CCDs were another advancement that came to astronomy, and they started being used in telescopes in the early 1980s and 1990s. By adding CCDs to make digital images, astronomers can now use computers to help search for moving objects. Instead of flipping back and forth between photographic plates, automatic pipelines could start to search for those tiny points of moving light instead. Remember, we don't usually resolve an asteroid in an image. We see a small dot or maybe a streak, but it's moving with respect to the stars. So this was a big advantage, even though most candidates still had to be checked by human eyes. And most candidates were in fact rejected because they were due to artifacts or mismeasurement of stationary stars, or just glints in the telescope, or even just noise. However, with these automated pipelines, larger dedicated surveys could be run, and run on bigger telescopes with larger CCDs as the technology continued to develop.
I just want to break in to say that photographic plates, you're using one piece of glass with photographic chemicals on it to make an image. And so this is probably foreign to any young person who,
That's true. That's
you
true.
know, because camera, film, what? And so this is even before the plastic film. But glass plates in astronomy were terribly important because they were flat. And that was important because if you had film that wasn't completely flat, not only the images wouldn't be in focus, you were measuring the brightness of these images sometimes by the diameter of the dots on the photographic plates. And then the big step when we start talking about CCDs, which are shorthand for charge coupled devices, basically these are electronic cameras, and these are the first cameras that are now taking images, and we're skipping photographic film and plates, and we're taking the images and digitizing them. So we're getting into the digital realm here that everyone on the planet's familiar with, because you carry a digital camera in your back pocket, and every young person has one with them, which is their cell phone. And of course, your cell phone is far more sophisticated than these early CCD cameras, but this is the beginnings of digitizing the images, and it's a very powerful step in astronomy. Thanks, Dr. Jones.
Yeah. No, and when we think of it today, we think, of course, this is an advantage, but especially at the early introduction of CCDs, they were much smaller cameras that they could the only cameras they could make were much smaller than the photographic plates. So in some ways, it was more convenient, and it let you do all of this digital processing. But it was also, we're giving up a large part of the sky that you could have seen within your telescope in order to be able to use these CCDs. Luckily, technology, moves forward, and now we have really large CCDs. But especially in the early parts of this time period, the 1980s and 90s, they were generally smaller, but you still see this big increase in the number of asteroids discovered in each year. So I marked the start date of some of the large asteroid surveys of this period on the plot. So the location, you can see Spacewatch, Linear, NEAT, LONIOS, CSS's Catalina Sky Survey, and the location left to right tells you when they started, and the location up and down, I try to indicate something about the relative number of asteroids discovered in that survey. It's worth noting that Spacewatch and Linear, two of the surveys which discovered the most asteroids, and still have discovered the most over time, were only operating with 1 to 2 meter class telescopes. This is a relatively modest class of telescope today. It would have been a good sized telescope at the time, not the largest, but a reasonable size. And their cameras were only capable of covering a few square degrees, but they could do that only by having very low resolution. Each camera was sort of on the order of about 4 megapixels. So that was not very high resolution. Still, these surveys drove the asteroid discovery rate up significantly, as you can see. Over 25 times more asteroids were found in the last 40 years than the entire 200 years previous. The rate of discovery of near-Earth objects, which is the orange part of the plot, increased significantly and consistently over that time period as well. So I've talked a lot about how quickly we were able to discover asteroids over time, and in particular how technological advances have driven asteroid discovery forward. But I haven't really talked about why we're doing this, what we can learn. So first, asteroids are physically generally rocky, and this is mixed with various amounts of metals, so minerals and silicates. When we say metals, that's what we mean. The composition of asteroids, what they're made of, can help us understand where these asteroids formed. And this lets us learn about the formation and history of the solar system. In other words, how planets form, which is generally something we're interested in. Second, asteroids have definitely impacted the Earth in the past. While most craters on the surface of the Earth are relatively rapidly wiped away by geological and weather processes, we can still see some. So Meteor Crater in Arizona is a striking and reasonably accessible example of one of these impacts. And the Chelyabinsk meteor that fell in 2013 is a very recent example of a much smaller impactor. So these impacts could deliver water, volatiles, like some of these minerals and lighter elements to the Earth, which could have helped life develop. And so studying near-Earth objects is helpful in understanding these potential effects and how much they could have influenced our biosphere. Third, impacts onto the Earth can still happen in the future. So the joke is the difference between the dinosaurs and us is that we have a space program and we might be able to do something about this, but that only helps us if we can find potential asteroid impactors before they impact. Hopefully long before, so we can deflect or mitigate any such effect. So I'm going to talk a little bit more about this last discovery effort now, in particular discovering near-Earth objects, as these are the only kinds of asteroids that are likely to impact the Earth. So in terms of impact hazard, not all asteroids are the same. First, the orbit has to be likely to impact the Earth. So we've talked a little bit about potentially hazardous asteroids. Even potentially hazardous asteroids are not necessarily going to impact the Earth. That distance cutoff is just an intersection with Earth's orbit. So you have to go out and look at the asteroids, track them through discovering and monitoring the asteroid to determine what the orbit is and if it has a risk of impacting the Earth. Secondly, though, the size of the asteroid also plays a part. Larger asteroids over 1 kilometer in diameter can trigger global level events in the case of impacts. So these were the first priority, to discover and identify any that posed any risk of impact. Being larger, they're also easier to find because they're brighter. Discovery of these large objects, which you can barely see on the plot because there's not a lot of them. This is the year of discovery and the number of asteroids that were discovered, near-Earth objects discovered. And in blue, way down here at the bottom, are the large, very large, over 1 kilometer size asteroids, near-Earth objects that have been discovered. The orange shows the next size down, and the green is the very small objects. So the discovery of the very large objects peaked in the early 2000s. And we think that we found almost all of these asteroids now, with perhaps 1 or 2 remaining based on models of survey efficiency. So we think we found all of the very large, over 1 kilometer NEOs, except for perhaps 1 or 2. And happily, we found that none of these asteroids pose an impact risk, which is very good news. That would be very bad if they were. The next risk level corresponds to asteroids about 140 meters in diameter or larger. So these would result in region-wide devastation in the case of an impact. Smaller effects would be felt throughout the world in terms of like global economies and so on. Discovery of these objects is ongoing, but you can see that these are the orange objects in this plot, where you can see that the level is kind of leveled off. So it's ongoing, but at a rate that shows that we will need bigger and better telescopes in order to complete this discovery effort within the next decade or so. And I say a decade or so because that's approximately the time scale that was laid out in a 2005 congressional mandate, which mandated that we find 90% of the NEOs larger than 140 meters in diameter. Meanwhile, discovery of even smaller objects, those are the objects smaller than 140 meters, that would be sort of, if they impacted the Earth, it would be a local event. But these objects are being discovered at an accelerating rate as more telescopes are spending more time on the sky. So more rapid sky coverage for these gives us more opportunities to find these smallest objects as they swing close by the Earth. As they get close to the Earth, they get much brighter than they would if they were further away, and so that makes them easier to find. And so the more time you're on the sky, happening to catch them coming by, the better for discovering these objects. So where does this my project fit in here? So I'm going to talk now about future NEO discovery. I may be a bit biased. I work for this project after all, but I think it's revolutionary next generation survey project. So the Vera-C Rubin is a new observatory being built to carry out the next generation survey, the legacy survey of space and time, the LSST. The LSST is a survey designed to carry out multiple science goals. The combination of these goals has driven the telescope design. So the 4 core science goals are to constrain models of dark energy and dark matter, to map the local volume of Milky Way, to explore the optical, transient, and variable sky, and to inventory the solar system, finding asteroids and comets that helps us study the formation of our solar system and identify those near-Earth objects which would pose a risk to Earth. The LSST will be revolutionary in each of these areas, and in particular, the LSST will discover about 10 times more objects in each population throughout the solar system and measure their orbits very accurately. In addition, the LSST will provide information on the object's physical characteristics, such as their composition and shape. So these science goals drive the observatory and telescope design, needing to detect NEOs and other quickly moving objects without trailing losses, as well as the desire to get many observations for transient and variable star studies leads us towards short exposures. Short exposures and still needing to see faint objects means that we need a big telescope. And wanting to cover large amounts of sky in each image so that we can rapidly cover the sky frequently means we need a large camera. So we also plan to run the survey continuously for 10 years, and that lets us get down to the very faint levels to be able to measure the faintest objects needed for cosmological studies. And then finally, because astronomers will also need to be able to access and use all of this very large data set in the form of catalogs, ideally, that means we also need very careful data processing pipelines, not only for finding asteroids, but also for measuring the properties of stars and galaxies. So I'll briefly go through the description of the telescope, of the observatory itself, the telescope. We have a big mirror, a 6.5 meter effective diameter mirror, which is a large telescope diameter for a survey telescope. You can see our primary tertiary mirror here on the left, surrounded by team members before the polishing process was started. They did not walk on a polished telescope to sit in the middle of that. On the right, you can see the mirror on its journey to the summit in Chile after it was polished. So it's currently in storage on site, waiting for the time to be installed. We have a very enormous camera to go with that big mirror. So the camera can cover 9.6 square degrees of sky in each image. That's 7 full moons can fit across the field of view. In addition, it's an extremely high resolution camera. The camera contains 3.2 gigapixels, so you do get the capability to see very tiny details, even though you have this very large image. To view an entire image at full resolution would require 1,500 high-definition TVs. And physically, the camera is large as well. It's about the size of a small car. So, like I said, we plan to run the survey continuously, and because it's a survey, it means that it's not like a classical telescope where you put in your proposal and you say, I want to look at this particular thing. We have a plan for how we're going to cover the sky, and we'll just do this continuously for 10 years, make those catalogs and make them available. At each point in the sky, we're planning to take 2 very short exposures back to back, so like 2 15-second exposures, and we call this a visit. We then return to the same point in the sky later, about 30 minutes later, for a second visit. We do this second visit so that we can detect moving objects, because you can see the move over that course of 30 minutes. And then we come back again within a few days, and while the objects that we're looking for are probably not necessarily in the same field of view, they're likely nearby. And so we look at the entire part of the sky, and that means that we can link these objects together if we see them, because we'll get observations of them again within a few days. So we continue surveying the sky in this manner for 10 years, and on the right is a plot of roughly where we expect to look on the sky. So we expect to cover most of the sky visible from our location in Chile. So The Rubin Observatory is currently under construction in Chile. We're working very hard on all of the data pipelines so we can get catalogs as well. You can see this photo is a recent photo of our dome, an auxiliary telescope. The Auxtel is on the right. We anticipate first light within the next year, and survey operations were unfortunately delayed somewhat due to COVID, but we should be able to start surveying sometime in late 2023. I wanted to touch briefly on what it means about discovering asteroids in the LSST data, just because there's so much of it. So basically, anything that can go wrong will, and we won't be able to confirm or reject candidates by eye because there will be too many candidates. In a way, identifying asteroids in images is like playing a game of connect the dots. However, you have to do it efficiently because there's a lot of data to get through. And there are a lot of other dots moving around, which may be other moving objects, maybe the same one, or maybe stationary things, or maybe artifacts in the images. And you don't know which dot should be connected to which other dot. So in this example here on the left, there's a small, faint moving object that I've circled, and there's pretty easy because I've circled it. And so you can see which object it is that's moving, and it's not moving very fast. When you need to do this and have it work on large scales, you need efficient algorithms. So one place to start is by doing what we call image subtraction. So we take a template image from a different time and subtract it from our new image so that you only see the things which have moved between the two or changed. This is complicated, of course, because the two images are not usually of the same quality, but it does help because it gets rid of a lot of those stationary objects and certainly all the galaxies. And then you still need to link those moving dots together. But like I said, astronomers have been working on this problem since the early 1980s. And as surveys have started taking more data, our pipelines have had to get better and better. With Rubin, and in the last couple of years at other telescopes as well, algorithms have really been moving forward in this regard, especially, computing power is getting larger and more available. With Rubin, we've developed a new software tool called HelioLink 3D that can do a more effective job at linking together the moving object detections. So this will be on top of better image subtraction software, which we also need to do a very good job at for all the other transient and variable science as well with asteroid detection. And finally, we will do orbit fitting to help determine if a candidate is a real asteroid or not. So this is all made possible, in particular the orbit fitting, because we're linking and fitting many observations within a short time span. And that comes back to our survey cadence and how we can survey the sky. So the time period we are trying to link observations over is long enough to see deviations in motion that would indicate we're not linking things correctly, but short enough to make the problem computationally tractable. And we're currently testing this on existing survey data such as the Zwicky Transient Factory. So what can we expect in terms of NEO discovery with Rubin Observatory? The LSST should discover on the order of 10 times more NEOs than are currently known. Currently, there's about 25,000 NEOs overall sizes. After 10 years of Rubin, I expect it to be on the order of 200,000 NEOs discovered, down to these very small sizes. The largest NEOs, these 1 kilometer and larger in diameter, will receive about 275 observations each on average over the course of 9 years or so. It's worth noting this isn't the full 10 years of the survey because NEOs have long synodic periods. That is, there's periods of time where you can't really see them from the Earth because they're behind the sun from our point of view. And this is one thing that makes them a little trickier to detect, and one reason that we have a 10-year survey and why that's advantageous. Because we have time to let the NEOs come to us as well. Smaller NEOs on the order of 140 meters in diameter will typically receive about 50 observations each over the course of 3 years. So here the window of time over which we can detect the object is shorter because as they move closer and further from the Earth, and then they become too faint to see in a single observation as they get further away. In each case, there are some asteroids which get more observations and some that get fewer, either because of chance or the way their orbit just syncs up with the observing pattern. Overall, however, this is interesting because it's enough observations to start to characterize the objects. So with enough observations, we can look for changes in their brightness that let us learn about their shape, if it's round or more elongated, for example. And because the LSST operates in multiple band passes, that is, we use a green filter and a red filter, is an example. We also obtain information about their color, which lets us put constraints on what they're likely to be made of, so we get information about their composition. These physical clues are helpful to help us understand more about NEOs in general, including information that would be helpful to understand how to deflect an asteroid if it did pose an impact risk. However, all of these mitigation and deflection techniques must start by discovering NEOs, preferably long before any potential impact, and evaluating their impact hazard. We did a small test where I simulated a subset of NEOs that actually were on impacting orbits. So this is not the typical NEO population. But what I find is that the typical warning time for an impactor in this simulation was about 5 years for a 140-meter diameter object. This isn't an extremely long period of time, but it is helpful, and that's only sort of the average. There are some which we would find earlier. At any rate, this is a great time to get cataloging these objects. And I'm going to end it here, but I thought you might like a few more links to resources if you're interested. The first link here is to Rubin Observatory and the LSST's website. The next one is to the B612 Foundation. They are doing work in various areas related to improving asteroid detection and impact hazard evaluation, as well as promoting Asteroid Day. And then the last one is the Center for Near-Earth Object Studies, CNEOs, which is a group run at JPL who do a lot of work on improving asteroid orbits and evaluating impact hazards for known asteroids. And they have a really fascinating webpage with a lot of this information about surveys that are discovering NEOs today. And finally, I'm Lynne Jones, and it's been my pleasure to give you this brief talk today.
Well, thank you, Dr. Jones. Before we segue into all the questions that have been pouring in during your talk, I do want to give a shout out to our sponsors. Thanks to Century Bank here in Cartersville, and also to Courtyard Marriott of Cartersville for generously helping support programming here at TELUS. And I'm going to segue into questions. First question is, can you tell us a little bit about Apophis? It's an NEO that's due 2029.
Right. So Apophis is interesting because this is where it gets a little bit complicated in terms of like what asteroids are an impact risk or what are not. So there are these things called keyholes, which are areas in space near the Earth where if the asteroid goes through the keyhole, it passes through this region of space in a particular way, then it's not going to hit the Earth that time, but the next time it comes around, it would. Potentially, that might be many, many years later. So Apophis is one of these that, and the problem with keyholes is that they are very specific, they're small, and the regions around them can mean either it will hit the Earth or it won't hit the Earth, and it will. They're chaotic regions basically at the edges. And so Apophis has been at the boundary of like, will it hit this keyhole in a way that it will impact the Earth after it passes through the keyhole, and or will it not? And I believe that recent observations have actually shown that it will not pass through the keyhole in a way that will lead it to impact the Earth in the next approach. But we don't know for sure about the approach to the keyhole after that, which would. This is where it gets it gets rather complicated. So, and I don't remember the exact dates of the approaches to the keyhole or what that means about impact time, unfortunately. But I do remember that with the new measurements. So basically, this is where we go out, and for objects which are impact risks, we go out and we take more observations, and we say so that we can measure the orbit more precisely. And so by looking at this object over and over again and getting more observations, we've been able to tell that no, it will not go through the keyhole in the way as to promote an impact at the next approach, and so it will not impact the Earth for the next 100 years. So that has been pushed off until a much further time at this point.
Another question is, if you've got an asteroid heading our way, it's going to be an impactor. What kind of strategies do we have to destroy or deflect an incoming asteroid?
Yeah, so this isn't exactly my what I work on, because I work much more on finding the objects. But in general, you have sort of two kinds of classes of missions. You have deflection missions where you go and you try and slowly influence the orbit of the asteroid. So this is where the things like the gravity tractor or changing the surface properties of the asteroid so that it changes its orbit, like painting one side of the asteroid, for example, come in. And the gravity tractor, you put a massive object in just the right place off of the near but not on the asteroid so that it changes the orbit slowly. Both the gravity tractor and things like changing the surface properties of the asteroid so that it interacts differently with solar radiation, which will then slowly change its orbit over time. These are very slow effects, and so you need quite a long time to make these deflection techniques work. How long you need would depend on the properties of the asteroid, in particular the mass of the asteroid, and certainly things like, is it a binary, is it very round, is it elongated? Then there's another class of deflection missions which are much more like hands-on, you might say. So these are basically like kinetic impactors, or preferentially, doing a nuclear detonation on one side of the asteroid, for example. And those can have potentially greater effects, but again, it depends on the properties of the asteroid. If you have a very fluffy, carbonaceous chondrite kind of low-density asteroid, and you try to impact it with a kinetic impactor, you might just break it apart and have it still be coming straight on the same original course, just now in lots of little pieces, rather than actually deflecting it. So in any and even in that case, it still would take a significant amount of time to change the orbit and deflect the object. However, there is an interesting test of a deflection technology ongoing shortly. It's called the DART mission, D-A-R-T, and it's pretty fascinating. I don't really have time to get into it, but it's basically, there's a binary asteroid. They're going to send a small impactor into the moon of the asteroid, and then look at the effect on the orbit. And they're able to tell the effect on the orbit by the fact that it is a binary asteroid, and so they can monitor the center of mass of the two.
I believe that mission's within the next year. They're sending that out. There was a kind of along that line, there was a question, do asteroids bump into each other and change their orbits by collisions?
Yes, but infrequently. It probably happened more frequently in the past. So we do think the asteroid belt was potentially more dense in the past, and that some asteroids have been lost, kicked out into the outer solar system is one place we think they've gone. But you see asteroid families, and these are evidence of collisions in the past, because the family is a group of asteroids that have related orbits and they have similar physical characteristics. And when you look at them, if you model the effect of like an asteroid splitting apart a long time in the past, a very long time in the past, you can see that they would spread out in their orbits in the way that we see the orbits are spread out in the same family. So these asteroid families are evidence of collisions that happened in the past in the asteroid belt. We haven't seen any lately. That would be, it's definitely something people are looking for, and there's a couple potential impacts of like a very small object onto a larger object that we've seen. But yeah, this is actually one of the things that I think the LSST will be really interesting for, because we look at the objects, the asteroids, so frequently and get so many observations of them. We'll be able to look for evidence of surface activity that could be the result of an impact.
Yeah.
Surface, I mean like dust and gas coming off the surface that you might have happen as the result of an impact.
I will say that Cartersville was the impact site of a very tiny piece of an asteroid about the size of a baseball that came through a house of just a few miles from the museum back in 2009, the Cartersville meteorite, and that's been identified as an object that came from the asteroid belt, and you can see it here at TELUS, by the way. And there was a piece in the paper today about an asteroid that it didn't list the name of the asteroid, that was somewhere between 300 to 800 feet across, that will be passing close to the Earth's orbit tomorrow. Can you tell us anything about that?
You know, I started to look it up because to see what this was about. What I do know is that it's a 2021 object, so it's been discovered very recently. I'm not surprised because it's also fairly small, and so generally objects which are very small and are coming near the Earth, we only find them because they're because of the fact they're coming so close to the Earth, and so they get brighter for us to see. And so yeah, this is a lot of these small asteroids whiz by, and you can actually follow a Twitter account that tells you about all the close approaches that are happening. This one is further away than the moon, and it doesn't pose any risk. It's just flying by.
A nice, gentle 13,000 miles per hour.
Yeah.
And finally, Dr. Jones, would you like to comment why International Asteroid Day is on June the 30th?
Ah, right. So International Asteroid Day is on June 30th to commemorate and remind us of the Tunguska impact, which was a rather large, medium-sized asteroid or meteorite that fell in Siberia. We think that one was on the order of a few tens of meters. So in the smaller range compared to some of the things we talked about, it flattened a large area of trees. Certainly would have been pretty devastating if it landed anywhere other than the middle of Siberia. And so it's a very interesting and very recent impact that sort of reminds us, yes, these things are still ongoing and are still at risk. And that's why Asteroid Day is on June 30th.
And that was in 1908, 1911? I can't remember exactly.
I can't exactly remember either. It's 1908 sounds familiar.
Anyway.
Yeah.
So,
very recent.
with the impact of that statement, I would like to thank you, Dr. Jones, for your time this afternoon. It's been a pleasure having you on Lunch and Learn, and thank you so much for being so generous with your time. And I know if folks out there have more questions, just email me here at TELUS, and I can forward them on to Dr. Jones, and I'm sure she'll be glad to answer more questions if you have more. And thank you again to our sponsors, Century Bank of Cartersville, and also Marriott Courtyard here at Cartersville as well, for their generous support. And thank you for tuning in this afternoon.